Students, there is one thing we need to do before we actually show that those operations are well defined, because we're going to need a lemma. The lemma is going to help tell us when two things are the same. So remember, what we have is we have this weird situation where we're looking at vectors plus a subspace, right? Things of the form x plus u. And this is what we're looking at. And what we want to know is are those two operations well defined? It might help to know when two elements are actually equal. If I have an x plus u and a w plus u, how do I know whether or not x plus u is equal to w plus u? So we have this criterion. And it says that let U be a subspace of V, then the following are equivalent. So we have three things we're going to show are the same. Or if one is true, the others are true. So number one is going to be that W minus X is in U. Number two is that the actual two elements, W plus U and X plus U, are equal. And number three, this is one that seems a little crazy, is saying that there's something in both. Okay, so going back and forth between 1 and 2 is already going to be really, really useful. We can sort of see that right off the bat. If I want to know that whether or not W plus U is equal to X plus U, all I have to do is take W minus X and see if it's in U. It sounds much easier than, say, drawing a picture. In some situations we can't draw a picture. It'll give us a nice, quick way of telling whether two things are equal. Even though W may not be equal to X, I just have to check, is W minus X in U? If so, then these two are the same element of V mod U in that quotient vector space. Okay, now this last one is actually kind of special. If you think about it, this is kind of incredible. It's saying if there's any one element in both of these, if there's anything in both, then they're identical. Okay, so anything at all in both of these spaces, we don't know their spaces yet, we know their sets. Anything at all in all of these sets, boom, we know that they're the exact same set. So that seems very strong. It seems like it might be hard to prove. Maybe, maybe not. Let's see. So, proof. Let's go from 1 to 2. Okay, so we're going to assume that W minus X is in U. So we'll assume that W minus X is in U. And let's start off by showing that the left, that's the right, that's not the left, this is the left, that W plus U is contained in X plus U. Remember, these are sets. This is a set of all the elements in U, each added to W. So W plus each of the elements in U. And this is the set of X plus each of the elements in U. Okay, so I want to show that this is contained in this. Okay, well, if, I don't really need to give another a letter, but let's say, I'll do it. If A is equal to W plus U, that means A is going to be W. So I need a trick to get an X in here, otherwise I'm going to be stuck. So that would be minus X plus X, because I can't just make an X, right? But what I could do is I can add the identity and its inverse. Okay. Let's do it like this, actually. If A is equal to W plus U, then there exists a U, little u. So A is equal to W plus U. Same trick, W minus X plus U, which is equal to X plus W minus X plus U. Okay, so if I have anything in this set on the left, then by definition there must be a U, so A is equal to this W plus U. I can't just add an X because I want an X to appear, but I can add and subtract an X. That's fine, I'm just adding 0, I'm adding the identity. And then I switch the order and I move this over to the right, and look, this is something, this is X, and this is something in U, because this is U and this is U, this is in U and this is in U. We're using the fact that U is a subspace. we better use the fact that U is a subspace. Because if we don't use the fact that U is a subspace, then this would be true for non-subspaces. So we're going to need to use the fact that U is a subspace at least somewhere. Okay, so we're using that U as a subspace. So that means that this is in X plus U, because this is X and this is something in U. Oh, what did I show? Thus, W plus U is contained in X plus U. And the other direction is the same. I could have said without loss of generality in the beginning and just gone in both directions, but the other direction is the same. Okay, so that's going to give me that W plus U is equal to X plus U. Okay, now 2 to 3, I don't like to use the word easy, but I do think that this is the most vacuous proof we have. Because what are we doing? We're assuming that W plus U is equal to X plus U. And that means we're assuming that every element of W plus U is in X plus U. And every element of X plus U is in W plus U. That's what we're assuming. Okay, what do we have to show? That there's one element in both. But I already know that every element is in both. So what I'm going to do is I'm going to pick any A in W plus U. And we know that since W plus U is equal to X plus U, since W plus U equals X plus U, A is also in X plus U. Oh, we're done. There's something in both. Ah, there's nothing else to write. Okay, that's the whole part. Okay, now 3 to 1. Now this is one that looks like it might be hard to prove. This one looks like it's going to be tricky, right? Because this is saying that there's something in both, and this is saying that they're exactly equal all the time. But what we're going to do is we're actually going to go from 3 to 1, and then this sort of completes the cycle, and we can get from any of these to any of the others. Okay? So what are we going to do? Let's assume. We're going to assume there is something in both. So assume A is in W plus U, and A is in X plus U. Okay, so what does that mean? Well, it means that A is equal to W plus some little u, I'll call it U1, and it's equal to X plus some little u, I'll call it U2, for U1 and U2 in U. Okay. What does this mean? All I have to do is this. Then, I'll write it then. Then W minus X is equal to U2 minus U1, but U2 minus U1 is in U because it's a subspace, and I am done. So that was actually really easy. So one more time, I said, hey, assume there's something in both. Right, what does it mean to be in W plus U? It means you must be of the form W plus something in U. What does it mean to be X plus U? It means you're of the form X plus something in U. I have this equals this. I subtract. Boom! That's what I have. So now we have this lemma. We can use it to tell when two things are equal in our quotient space that we haven't proven is a space yet. We're going to call it the quotient space. Right now we just know it's a set. But that's the next thing we're going to do is we're going to move forward, and now we can try to show that those operations of addition and scalar multiplication are both well-defined. That doesn't mean which element I take, as long as I get things that are equal as sets, I'm going to get the same outcome after I scalar multiply or after I add.